Swayam Prabha. Digital India. Educated India.
Welcome to the third lesson of the seventh module, which is on deflection of beams part 3. In fact, in the last two lessons on deflection of beams, we have discussed how the deflection of beam affects in general and why do we need to evaluate the deflection in beams and consequently the slopes in the beams. Now, in this particular lesson, we are going to look into some more aspects of deflection. In fact, in the last two lessons we have discussed the differential equation of the elastic curve and consequently we have derived the the equation for the elastic curve. Now, here we will look into another methodology which we call as the moment area method to evaluate the slope and deflection in beams. Hence, it is expected that once go through this particular lesson, one should be able to understand the concept of moment area method in evaluating slope and deflection of beams, and one should be in a position to evaluate slope and deflections in different types of beams for different loadings using moment area method. In fact, in the last two lessons we have solved quite a few examples wherein we have used the differential equation for the elastic curve and we have derived or we have evaluated the equation for the elastic curve, based on which we could evaluate or estimate the deflection in a beam at a particular location. Also, we could compute the value of the slopes wherever needed along the length of the beam. Now, in this particular lesson we are going to discuss that if we employ this particular method which is called as moment area method, then how do we compute the values of the slopes and deflection in beams. Hence, the scope of this particular lesson includes, we will recapitulate some aspects of the previous lesson. It includes the concept of moment area method, it includes moment area theorems and their application. In fact, based on this moment area method, there are two theorems which we call as moment area theorems, and we will state those theorems and consequently we will look into how they are applied in evaluating slope and deflection in beams. And then we will look into some examples for evaluation of deflection in different types of beams for different loadings. Now, let us look into the questions which were posed last time. The first one is, what is flexural rigidity of beams? Explain. Now, let us look into this aspect. We had indicated in the last lesson that EI, this particular parameter EI, is known as flexural rigidity, where E is the modulus of elasticity of the material we are using for the beam and I is called as the moment of inertia of the cross section taken about the neutral axis. This is the moment of inertia about neutral axis. Now, let me explain this with reference to a simple example. We have seen that for a simply supported beam which is subjected to uniformly distributed load of intensity Q per unit length over a length of L, the deflection which we get, the maximum value of the deflection as 5 Q L to the power 4 by 384 EI. Now, let us assume that we have two beams which are identical, that means they have the same length, they are subjected to the similar intensity of the loading which is Q, and they are made out of the same material, so that the value of E is same for both the beams. Now, the only difference between these two beams is that in this particular case we choose a cross section. Let us say that we choose a section of which is a rectangular section, the width of which is B, and let us call depth as H1, and for this particular beam we choose a cross section for which width is B, but the depth is H2, and let us assume that the depth H1 is greater than H2. Now, since all other parameter like Q, L, E, they remains constant, then the parameter which is changing because of the change in the depth is I, because I for this rectangular section is equals to B H cube by 12. So, with the change in H, there will be change in I, there will be change in the deflection delta. Now, physically if you look into that, if you take a beam which is having a depth larger than the other one, having other parameters constant, then larger the depth, the more the beam will have more strength, and physically given the identical situation, the larger depth of the beam will be in a position to carry more load, or in other words, if we keep the same load for both the beams, the beam which is having larger depth will deform less. So, we can call the beam which is having larger depth in comparison to the other. So, the other beam, the larger depth beam is more rigid in comparison to the other beam. Hence, the value of I, if E is constant, then E I, this parameter governs the delta, since other parameters remain constant. Now, if the value of E I is higher, then the value of delta will be less, and the vice versa. If E I becomes lower, then delta will be more, and physically that is justified. That means, if E I is larger, means for the same material, for same E, I value is more, that means it is more, the cross sectional size is more, and it is naturally going to carry more load or going to deform less, and consequently you will get less deformation, which is delta. Hence, this particular term E I in fact physically signifies that how rigid a member is, given the cross sectional parameter known to you. Hence, this particular term, since flexure as we have seen comes from the bending of the beam, which we call as a flexure as well, it is a flexing of the beam, and hence this particular term E I, which defines the rigidity of the beam against this flexural action, we call E I as the flexural rigidity, and that is the significance of this flexural rigidity in computing the deflection or the slope, which we call as the deformation of the beam against lateral loading or the transverse loading. Now, the second question was, what is meant by M by E I diagram. Now, this is interesting, and this with reference to this present lesson we will be discussing in more detail. Now, let us look into what is really meant by M by E I diagram. Now, as the terms you are acquainted with, that particular value M or particular designation M, we generally designate bending moment in the beam as M. So, basically when we are saying M by E I diagram, that means it is related to the bending moment diagram. Now, again coming back to the example of a simply supported beam with a uniformly distributed load, which is subjected to Q per unit length. Here, as we have seen, that the bending moment varies parabolically over the entire length, and this particular diagram represents the bending moment diagram, the maximum magnitude of which is Q L square by 8. If we compute this ordinate, we will get as Q L square by 8. Now, when we say M by E I diagram, what we mean is that each and every ordinate of this bending moment diagram, if it is divided by the flexural rigidity of the beam member, which is E I, then we will get another diagram which is similar to the bending moment diagram in nature, but we will have the different values of the ordinates, which is equals to m by EI. The m value which we will have for the previous diagram, for the bending moment diagram, the m by EI diagram will be having ordinate value which is lower, because we are dividing each of the ordinates of the bending moment diagram by the term EI. Hence, the magnitude, the maximum magnitude over here for the m by EI diagram will be QL square by 8 EI, whereas the magnitude of the bending moment at this ordinate will be QL square by 8. So, this particular diagram where we divide all the ordinates of the bending moment diagram by EI, we call that as m by EI diagram. Now, it may so happen that in this particular case we have considered that EI value is constant throughout the beam. Now, it may so happen that we have a beam wherein the central part is having larger value of EI, thereby here as if you have the larger cross section over the rest of the beam, and let us say if you have a moment of inertia of 2I and other places we have the moment of inertia of I, then the value of the flexural rigidity in this zone is EI, in this zone also is EI, whereas in this particular zone it is 2 EI. So, when we but the bending moment diagram remains as it is, like in this form. Now, if the ordinate, each of these ordinates are divided by the respective EIs, here it is EI and here it is 2 EI, then accordingly the m by EI diagram will change and we will have similar to this kind of a figure. That means, we will have here it is divided by EI, at this point it is divided by 2 EI, hence the value will be less, and then again it will go in this form exactly in the same orientation, and again it will come in this form. So, depending on the value of the moment of inertia and consequently the flexural rigidity EI, the m by EI diagram will change. So, this particular diagram we called as m by EI diagram, and we will see, we will make use of this m by EI diagram while discussing this moment area method for evaluating the slopes and deflection of beam, as we will go along in few minutes. Now, the last question which we had was that what is the deflection, the maximum value of the deflection of a simply supported beam which is subjected to a concentrated load at the center. Now, this particular problem or this example we have solved last time, and we have seen that if we employ the differential equation for evaluating the deflection curve or the elastic curve, which is EI d2y dx2 is equals to bending moment m, then we get the expression for elastic curve y as a function of x, and there if we substitute x for L by 2, then we get the value of y, which is maximum in this particular case because it is symmetrical with respect to the supports and with reference to the loading, and at this point if we draw the tangent to the elastic curve, this will be horizontal. Hence, this is the maximum deflection, and delta max we get as PL cube by 48 EI, where P is the concentrated load, L is the span of the beam, and the load is acting at the midway between the beam, which is at L by 2, and EI is the flexural rigidity, which is constant throughout the length of the beam. Well, then having looked into this, let us look into some aspects of this moment area theorems. Now, moment area method basically is a method for evaluating the slope and deflection for beams which are subjected to different kinds of loading. Now, in the last two lessons we have looked into that if a particular type of beam, that means it has some kind of supports, either simple support or a cantilever beam, when they are subjected to different forms of loading, either uniformly distributed load or concentrated load, we have seen how to evaluate the slope and deflection by using the differential equation for the elastic curve, and consequently by integrating the differential equation of the elastic curve after writing the expression for the bending moment, we have computed the expression for elastic curve, and based on the expression of the elastic curve we could compute the value of the deflection at different point along the length of the beam. Now, we are going to look into another method which we call as a moment area method, and as the name signifies, we are going to make use of the bending moment diagram of a beam, and in fact in this sense this is semi graphical in nature, that we will make use of this bending moment diagram in evaluating the slopes and deflection of the beam. Now, in deriving the equations or the differential equations for elastic curve, we had assumed that the beam material is linearly elastic and the slope is small, so that we could make some assumptions. Now, while deriving this moment area theorems, here also we make the similar assumptions. That means, the material is linearly elastic and the slope is sufficiently small, so that we can employ these moment area theorems in evaluating the slopes and deflection. In fact, there are two theorems for this moment area method, which we call as first theorem of moment area and the second theorem of the moment area, based on which these two theorems we can compute the values of the deflection and the slope in a beam. Now, the first theorem, first moment area theorem goes like this, that the angle between the tangents to the deflection curve at any 2 points on the elastic curve is equal to the area of the m by EI diagram between those 2 points. So, this is the first theorem says that the angle between the tangents to the deflection curve, that is the elastic curve, at any 2 points is equal to the area of the m by EI diagram. Now, let us see that how really do we apply this theorem in evaluating the or making use of this m by EI diagram. Now, in this particular figure, let us say that this is a part of the deflection curve and we choose 2 points A and B, and at point A we draw a tangent, so that this gives the slope of this particular point of the elastic curve, which we call as theta A. Now, if we draw a tangent at B of the elastic curve, now this particular tangent gives us the slope of this elastic curve at point B, which we have called as theta B. So, this particular angle is the difference of these two angles theta B and theta A, and this we call as theta B A, which is theta B minus theta A. Now, and this is the part of the bending moment diagram, and let us call this as now m by EI diagram. That means, the bending moment diagram has been divided by the term EI to obtain the m by EI diagram. Now, on this elastic curve or along the axis of the beam, we choose a small length dx, and on the elastic curve we choose this length as ds. Now, if we draw normal to this end of this ds, this particular length is ds, this goes to the center of curvature and rho being the radius of the curvature. Hence, let us assume that this particular segment ds forms an angle of d theta at the center. So, this length ds can be written as rho times d theta. So, ds is nothing but equals to rho d theta. Now, since this deformation is small and the slope is small, we assume that dx is equals to ds. So, in place of ds we write dx. So, rho d theta is equals to dx, or d theta by dx is equals to 1 by rho. Taking this term on this side and dx on this side, d theta by dx gives us is equals to 1 by rho. Now, you have already know from the bending equation that m by I is equals to sigma by y is equals to E by rho. So, if we take the relationship between m by I and E by rho, then 1 by rho is equals to m by EI, and that is what has been used over here, that 1 by rho is equals to m by EI, and therefore, d theta by dx can be related to the m by EI. D theta dx is equals to m by EI, or in other words, d theta is equals to m dx by EI. Now, if you look into this particular expression, now for this particular segment ds at the two ends, if we draw the tangent, let us say these are the two tangents, since these are the normals at the end of ds. So, and since this angle is d theta, hence this particular angle also is going to be d theta. Now, it demonstrates that the change in angle between these two ends of this segment ds, which is d theta, this is nothing but equals to the area of the strip which is on the bending moment diagram, the area of this particular strip, the ordinate of which is m by ei and the width is dx. So, m by ei multiplied by dx is nothing but the area of the m by ei diagram over this small strip ds, and that gives us the change in angle d theta between the two ends of this particular segment. Now, if we integrate this particular expression over the stretch a to b, then integral d theta a to b is equals to integral m dx by ei between a to b, and if we integrate d theta from a to b, we get this as theta b minus theta a, and which is nothing but equals to theta b a, and theta b a then gives us integral m dx by ei between a to b. Now, this means that this is the area of the m by ei diagram between the two points a and b which we have chosen on the elastic curve, is the area of the m by ei diagram between those 2 points. So, you see now what we are getting is that the change in slope between 2 points on the elastic curve, between 2 points as we have chosen b and e, and theta b a is the difference in slope between b and a, which is theta b a, is nothing but equal to the area of the m by ei diagram between those 2 points. So, you see this particular theorem demonstrates that if we know or we can physically plot the elastic curve of a beam, and if we are interested to find out the difference in slope between 2 points on the elastic curve, then simply if we can compute the area of the m by ei diagram between those 2 points, that will give us the value of change in slope between those 2 points. So, by making use of the bending moment diagram, or in other words m by ei diagram, we can readily compute the values of the slope of the elastic curve at different points, and that is one of the advantages of this particular method. Now, of course, while using this particular method, we will have to be careful that the diagrams which we get for the bending moment diagram, they are to be simple enough, like if you have a form like rectangular or square or triangular form or a parabolic form, for which we know the areas, we can compute the values, area values directly for such diagrams, and it becomes easier to implement. Now, let us look into some of the aspect of this particular theorem. Now, here if you note that we have used the term m, now that is for the bending moment, and the value of the bending moment could be positive or negative, or rather its sign will be as usual, which we have assumed earlier. That means, if you have a counterclockwise moment will give you the positive value of bending, and the clockwise moment will give you the negative value of the bending. So, we follow the usual sign convention as we have used so long. Also, now area of m by ei diagram is an algebraic quantity. That means, if we are choosing m by ei diagram between 2 points, and if it so happens, say for example, we have the m by ei diagram which goes like this, I am choosing arbitrarily. Now, if I am considering these two sections, let us say this is positive and this is negative, then depending on the sign as we have between these 2 points, we must consider these signs. So, the area of the m by ei diagram is given positive or negative sign depending on whether the bending moment is positive or negative. But when we try to compute the values of the slope or the value of the deflection, we really generally do not bother about these signs. Since we know physically how, because of the loading, how it is going to deflect, we can we just compute the absolute value, and then accordingly we assign the sign depending on whether it is having a clockwise movement or counterclockwise movement, or how the deflection is going, whether it is above the baseline or below the baseline, but only we are interested to evaluate the magnitude of these quantities, the slopes or the deflection. So, however, this sign convention is generally ignored, and only absolute values are considered for evaluating theta and delta. So, this is what is important while using this moment area theorem. Now, the second moment area theorem states that the tangential deviation of any point with respect to the tangent at any other point on the elastic curve is equal to the first moment of the area of the m by EI diagram between those 2 points evaluated with respect to the former point. So, it is again the tangential deviation of a point with respect to another point on the elastic curve. This is equals to the first moment of the area of the m by EI diagram between the points under consideration, and the moment is to be taken with respect to the first point where we are evaluating the tangential deviation with respect to the other. So, with respect to the former point. So, this is the second moment of moment area theorem, and let us look into how do we apply this theorem in evaluating the information as we need for evaluating slope and the deflection. Now, again we consider a segment of the elastic curve, and on this segment we choose 2 points A and B, and we draw a tangent at point A, and from B we drop a vertical line, and let us say this tangent cuts this vertical line at B1. So, in fact from B1 is the tangential deviation of B with respect to the tangent drawn at A. So, the second moment area theorem states that the tangential deviation of a point with respect to the tangent drawn from any other point is equals to the moment of the m by EI diagram between those 2 points and taken about the former points. So, the moment of this m by EI diagram between 2 points A and B taken about B will be the case as per this second moment area theorem. Now, let us look into this. Now, if we go exactly in the same way as we have done earlier, that means for the first moment area theorem, now here we choose a small segment say of length ds, and as usual this makes an angle of d theta at the center, and considering that this is a small deformation problem or the slope is small. So, this ds length we approximate as dx, and at the end of this ds if we draw the tangent, we assume that this cuts this vertical line, and we call this length as dt. This length BB1 where this tangent from A cuts the vertical line from B, BB1 we call TBA, and this small segmental length we call this as dt on line BB1. And since this deflection is small, the slope is small, so the axis of the beam, the distance x1 as we have chosen, the distance of the strip ds from B which is x1, we assume that the length dt can be computed in terms of this x1. Now, as we have seen that if this angle is d theta, this angle also is d theta between the 2 tangents. So, this is d theta. Hence, if we call this length as x1, so x1 times d theta will be dt. So, this is what is written over here, the dt is equals to x1 times d theta. Now, here we have assumed that slope is small, and thereby the length x1 which is along the axis of the beam is equivalent to the tangent length which is cutting the vertical line BB1 and giving the distance dt. So, dt is equals to x1 times d theta. Now, we have seen that d theta in the previous theorem, the d theta is equals to m dx by EI. So, in place of d theta if we substitute m dx by EI, we have dt is equals to x1 times m dx by EI. So, it shows that the distance dt between the 2 ends of this segment ds is m by EI, again is the ordinate of this particular strip. Now, m by EI times dx is the area of this particular strip of length dx, and if we take the moment of this area with respect to the point B is x1 times this area, that is what is the dt. So, if we integrate that dt from A to B, which will give us eventually BB1. So, T at P minus T at B1 is equals to TBA. This is equals to x1 times integral x1 times m dx by EI between A to B, this indicates that this is the moment of the m by EI diagram between points A and B taken about the point B, and integral x1 dx basically is the m by EI is the ordinate, dx integral over the length and the distance of that. Now, this point is the CG of this particular part of the m by EI diagram, and let us call that distance as x bar. So, this area times x bar, and x bar, mind that, is with reference to the point B for which we are evaluating the tangential deviation, is the moment of this particular area. So, the tangential deviation of B with respect to the tangent drawn at A, which is TBA, is equals to the moment of the m by EI diagram between B and A, and the moment is taken about the point B. That is the statement of the second moment area theorem. So, now that as we have seen that we have two theorems of moment area method. In the first theorem says that if we are interested to evaluate the difference in slope between 2 points of the elastic curve, then that is equals to the area of the m by EI diagram between those 2 points. And the second moment area theorem states that if we are interested to find out the tangential deviation of a point on the elastic curve with respect to the tangent drawn on the other point with reference to that other point, then that is equals to the moment of the m by EI diagram between those 2 points A and B, and the moment is taken about the former point which is B. That will give us the tangential deviation of the elastic curve or the point with reference to the other point where we have drawn the tangent. Now, we make use of these two theorems to evaluate the values of the slope and the deflection at any point in the beam, as we have done in case of using the differential equation for elastic curve, that we have written down the expression for the bending moment, we have employed the differential equation, we have integrated it, and we have computed the value of y at different points. Now, we will make use of this semi graphical method by employing the bending moment diagram to compute the value of the slope and the deflection in beams for different types of beams with different kinds of loading. But please keep in mind that moment area method becomes useful or suitable when the bending moment diagrams are relatively simpler. Like if you have a regular diagram like a square one or rectangular one or a triangular one or a parabolic configuration, for which you can readily evaluate the value of the area, and consequently you can take the moment of those areas with reference to the point where you are evaluating the tangential deviation. So, moment area method can be employed to evaluate the values of the rotations or the slopes and the deflection at any point in the beam. Now, let us look into some of the examples so that this becomes clearer. Now, before we go to the examples for evaluating the or for using the moment area theorem, let us look into the example which we did in the last lesson. And in the last lesson we did this particular problem, that we have a cantilever beam in which we have a load at the tip of this cantilever beam, which is a concentrated load. Now, what we had to do was to arrive at the equation of the elastic curve and deflection and rotation of the free end. Now, as we have seen that we could arrive at the elastic curve based on the equation of the differential equation of the elastic curve, which is EI d2y dx2 is equals to moment, and moment here we first compute the reactive values, the vertical reactive value, the horizontal one, and the moment, and based on these reactive values the moment at any segment, if I take a cut over here, we get the value of the moment as p into x minus p into L, and this if we employ, then we get the expression of the differential equation as this, EI d2y dx2 equals to px minus pl. Now, if we integrate this, then we get EI dy dx is equals to px square by 2 minus plx plus c1, and subsequently if we integrate this once again, we get EIy is equals to px cube by 6 minus plx square by 2 plus c1x plus c2. Now, for evaluating these two constants c1 and c2, we need to employ the boundary conditions, and as you know that at the fixed end at x equals to 0, at the fixed end both the slope and the deflections are 0, and the fixed end being at x equal to 0, at x equal to 0 y is equals to 0, and at x equals to 0 dy dx also is equals to 0. Now, if you substitute these two boundary conditions at x equals to 0 dy dx equals to 0, this gives us that C1 is equals to 0, and at x equals to 0 y equals to 0, if we substitute we get C2 equals to 0. So, this gives us that the value of the deflection curve or the elastic curve EIY is equals to Px cube by 6 minus PL x square by 2. Now, if we like to compute the value of the deflection at the tip, which is at x equals to L, we substitute the value of x equals to L over here, then we get PL cube by 6 minus PL cube by 2, and eventually we get PL cube by 3i. Delta is equals to minus PL cube by 3i, and we get minus sign because it is in the opposite direction of positive y direction. So, this is the value of the delta which we get. Now, eventually if we compute the delta, the maximum value of delta we get is at the free end of the beam, and that is the value of delta L, which we call as the maximum delta or delta max. Now, when we like to compute the value of theta at L, that means if we take a tangent to this elastic curve at this particular point, then here the tangent to the elastic curve is along the axis because it is parallel or along the line of this particular axis. Hence, this gives us the value theta b, because theta b minus theta a is 0 here. So, this is theta b, if we call this as a and this as b. Now, the value of theta b or theta L at x equals to L, if we substitute here at dy dx, since C1 is equals to 0, so it will be PL square by 2 minus PL square. So, that will give us PL square by 2, and if we divide by EI, then theta is equals to PL square by 2 EI. So, this is the value of the slope of the elastic curve at the free end, and this is the value of the deflection of the free end of the beam, which is subjected to a concentrated load. Now, as I have told you that from the governing equation, which is EI d2y dx2 equals to bending moment m, we had derived the different form of the differential equation. That means, if we take the derivative of that particular differential equation once again, we get EI d3y dx3, which is equals to CR, and as we know that V is equals to minus dm dx. So, EI d2y dx2 is moment m, EI d3y dx3 is dm dx, which is equals to minus V. Now, we can employ this particular form of the differential equation as well, and we can get the solution again in the same form. So, if we do that, then how do we go about it? Now, let us look into that. Now, here we have computed the values of the reactive forces R and the moment m. R is equals to P. Now, if I take a cart over here, if we take a free body diagram, here you have R, you have moment, and at this cart you have the shear force V and moment m. Now, this R is equals to P. So, if we take the vertical equilibrium of the forces, then V plus P is equals to 0, or V is equals to minus P. That is the shear which we have, and that is from here to here you get the same value. Now, if we say that EI d3y dx3, this is equals to minus V, this is equals to, since V equals to minus P, this is equals to P, or if we integrate this, we have EI d2y dx2, this is equals to Px plus C1. Now, at this stage, if we like to find out the value of C1, now we see that at x equals to L, that means at the free end, the moment is equals to 0. Now, if we substitute that particular condition, we get that C1 is equals to minus PL. Now, if we substitute the value of C1 over here, we get EI d2y dx2 is equals to Px minus PL, and that is the point where we had started that m is equals to Px minus Pl, and then we had integrated after substituting in this differential form, and we have obtained these values. So, even if we start from this particular expression that ei d3y dx3 is equals to minus b, we arrive at the same value. So, you can employ any of this form of this governing differential equation, that means ei d2y dx2 is equals to the bending moment m. Now, you can employ the other form of the differential equation as well, which is ei d3y dx3 equals to CR, which is convenient in this particular case, or if you have a distributed loading over the entire span of the beam, you could use ei d4y dx4 is equals to minus q as well, which we had seen in case of a simply supported beam subjected to uniformly distributed load. So, any of these forms of this differential equation according to the suitability, you can use it, and the final form of the results which will you get for the value of the maximum deflection or the rotations at different points, you will have the identical results. Now, let us look into another example problem. In fact, this example also was given to you last time, and in the last lesson we have discussed that if a beam is subjected to several loads of different forms, like if you have uniformly distributed load, you have several concentrated load on a beam, and if you are interested to find out the displacement at any point or the deflection of the beam at any point in the length of the beam, then the method which we have discussed so far, that means we compute the bending moment at different segments and substitute in the differential equation, and we solve the differential equation in those different segments, apply appropriate boundary conditions in those segments, and arrive at the final form of the elastic curve. We can employ the same technique for evaluating the deflection for multiple loads, or else what we can do is that we can apply the method of superposition. Means that we assume that instead of all the loads acting simultaneously, we split it. We assume that the beam, first as if it is subjected to uniformly distributed load, secondly it is subjected to a concentrated load alone, and several such concentrated loads individually they are acting, and for each of these cases we compute the deflection at the point where we are trying to find out the deflection for individually, and if we sum them up, then we get the identical value of the deflection as we were getting earlier. The reason behind this is that the deflection which we are computing is a linear function of the load which we are applying, and hence this superposition is valid, and you can get the deflection by using this superposition technique. Now, let us look into this particular problem, that first if we compute it the way we are computing now, and subsequently if we impose the method of superposition, then what happens. Now, you see here in this particular beam we have the concentrated load and the uniformly distributed load, which is q per unit length, and as usual we compute the values of the reactive forces. Since we do not have any horizontal load in the beam, so value of HA, the horizontal reaction at A, is equals to 0. Hence, we have the values of RA and RB, which is equals to, and this being symmetrical, you can make out readily from here that Q times L is the total load, that divided by 2 will be distributed between RA and RB, and the concentrated load P half will go over here and half will come over here, and that is what it is, that QL by 2 plus P by 2 is the value of the reactive forces RA and RB. Now, here we have two segments, this is segment 1 and this is segment 2. Now, for the segment 1, if we take a cut over here and draw the free body of the left hand, then the expression about the bending moment comes as RA times x, which is QL by 2 plus P by 2 times x, minus the uniformly distributed load over a length x, which is Qx square by 2, and this is valid between the range 0 to L by 2, x is between 0 to L by 2. Now, subsequently if we take the other part, segment 2, if we cut over here and draw the free body of the this part of the segment, which is at a distance of x, then the value of the moment is equals to again RA times x, which is QL by 2 plus P by 2 times x, minus Qx square by 2 because of this uniformly distributed load, minus the effect of this concentrated load, which is at a distance of L by 2 from at the 0, 0 point. So, this is x minus L by 2, and this is valid between L by 2 to L. So, L by 2 is less than equal to x less than L. So, these are the two expressions for the bending moment at two different segments. Now, incidentally, since this is a symmetrical beam or a beam which is having symmetrical loading, hence if we can compute for this segment, the other segment also will follow the identical results, but with a mirror image. Now, if we take the first segment and apply this in the differential equation, which is E I d2 I dx2 is equals to moment m. So, here q L by 2 plus p by 2 into x minus q x square by 2, that means we are taking the first part of it, the moment expression which is valid into the first segment, and if we integrate this, we have E I dy dx is equals to q L by 2 plus p by 2 and x will give x square by 2 minus this is x cube by 3. So, this is q x cube by 6 plus c 1, and on further integration of this we have E I y is equals to q L by 2 plus p by 2 x cube by 6 minus q x 4 by 24 plus c 1 x plus c 2. So, this is the expression for the elastic curve, where we have the unknown boundaries C 1 and unknown constants C 1 and C 2, which are to be evaluated applying the boundary conditions. Now, since we are using only the first segment, so we should impose the boundary conditions which are valid within that first segment. Now, if you look into that at x equals to 0, that means at this particular support that deflection is 0. Also, if we draw the elastic curve as we are expecting, this is being a symmetrical beam, that means a beam subjected to a symmetrical loading. Now, if we draw the tangent to the elastic curve at this particular point at the halfway point, that becomes horizontal. That means the value of the dy dx at x equals to L by 2 should be equals to 0. Now, if we substitute that x equals to 0, y equals to 0, we get that C2 equals to 0, and if we substitute that at x equals to L by 2 dy dx is 0, then from this expression we can get the value of C1, and eventually C1 comes as at x equals to L by 2 as 3 p L square plus 2 q L cube by 48 with a minus sign. So, the value of or the expression for the elastic curve, which is E I y, is equals to q L by 2 plus p by 2 x cube by 6 from here minus q x 4 by 24 from here and C 1 times x. So, C 1 is minus 3 p L square plus 2 q L cube by 48 times x. So, this is the expression for the elastic curve of the beam. Now, since we are interested to find out the deflection at the center, which is eventually going to be the maximum deflection, because this beam is subjected to the symmetrical loading both in terms of the uniformly distributed load as well as for the concentrated load. It is symmetrical, hence we expect that the maximum deflection will occur at the center of the beam. Now, if we compute the value of y at L by 2, this gives us a value of minus QL4 by 384 plus PL cube by 48, and in fact, if we take EI on the other side, we get y at that point this divided by 1 by EI. Now, if we try to apply, so this is the normal way, the way we are computing the value of deflection in a beam using the differential equation for the bending. Now, if we like to employ the method of superposition, let us see what we get applying the method of superposition for this particular case. Now, here this particular beam or this particular loading on this beam can be divided into two parts. In the first part, we take the beam subjected to the load which is q per unit length, and in this particular part we consider the beam which is subjected to the concentrated load P. Now, as we have seen that when a simply supported beam subjected to a load q, uniformly distributed load q per unit length, then for that the values of the maximum deflection at the center is equals to 5 QL4 by 384 EI, and the values of the slope at A and at B, which is theta A and theta B, is equals to QL cube by 24 EI. Now, here of course, we have not given the sign of the slope. Now, as you have noticed earlier that if you take the deflection curve, now the slope at this point is a clockwise one which is negative, and the slope at this end is anticlockwise which is positive, but the magnitude wise there this QL cube by 24 EI. Now, if we consider this particular beam where we have the beam with a concentrated load P at the center, then correspondingly we get the value of delta as PL cube by 48 EI, and correspondingly the values of the slope at A and B, if we compute it, this is theta A and this is theta B, they are PL square by 16 EI. Again we have not used the sign, only we have taken the magnitudes of those slopes. Now, as you can see that if we combine these two deflections together, that means since this particular beam we are analyzing and this beam is consisting of these two system of loading. So, if we compute the deflection which we have computed here and here, if we sum them up, that will give me the result for this particular case. So, total delta for this beam will be this plus this, which eventually we have seen in the previous case, and also the value of the slope will be sum of these two, which is that of this plus this. So, from by employing this superposition technique, we can split the loading system of a beam where it is subjected to several loads, either in the form of uniformly distributed load or in the form of concentrated load. We can split the loading system in the beam in different forms or in a simpler form, and then we can compute the values of the deflection and the slope at the point where we desire, and we can sum them up to get the results for the loads which are acting simultaneously. And this is the final form of this result for this particular case, that delta max is equal, this is for the uniformly distributed load, this is for the concentrated load. So, combined effect of this is the value for delta max over here. Theta at A is the effect of the uniformly distributed load and concentrated load. Again, theta at B is the effect of uniformly distributed load and concentrated load. Again, these are with the magnitudes, but not with the sign. Now, we have another example problem. Now, here we use the moment area method. In fact, this particular problem we have already solved to find out the slope and deflection of the free end. Now, we employ moment area theorem so that we can compute the values and check whether they are coming the same. Now, when we employ when we like to find out the delta, the deformation of this, that means if we draw a tangent to the elastic curve at this and if we drop a perpendicular, so this is the distance which is delta max, or which we call as TB. Now, so and also we are interested to find out the slope of this particular beam at this free end. If we draw a tangent over here, if we draw the tangent over here, this slope is 0. So, the difference between these two slope is theta b again. Now, as per the moment area first theorem, that if we are interested to find out the change in slope between these 2 points, it should be equal to the m by EI diagram between these 2 points, and that is what is considered over here. The bending moment diagram for the cantilever beam subjected to this tip load P will be PL by EI is the magnitude over here, and then gradually it will be coming to 0 linearly. So, we will have a triangular configuration for the m by EI diagram. Now, if we take the area of the m by EI diagram between these 2 points between A and B, which is half times PL by EI times length, that will give us the change in slope between these 2 points, which is equals to theta b, and that is equals to PL square by twice EI. Also, now when we draw a tangent over here, this is the tangential deviation of the elastic curve of this particular point, which is equals to the delta max. So, that means if we take the moment of the m by EI diagram with respect to this point, we are going to get the value of the deflection. So, delta max is equals to half PL by EI times L times the distance of the CG from here is 2/3 of L. So, if we employ that, that gives us a value of PL cube by 3 EI. So, these are the values which we have obtained earlier by employing differential equation. We can make use of this moment area theorem as well to get the values of the slope and the deflection. Well, we have another example problem. We will have to employ the moment area theorem to find out the slope and deflection of this particular beam, and this problem is set for you. We will discuss in the next class. Now, to summarize then, in this particular lesson we have included the recapitulation of previous lesson. We have looked into the moment area theorems. We have evaluated slope and deflection of beams using moment area method. Also, we have demonstrated some examples to evaluate slope and deflection of different types of beams for different loadings. Now, these are the questions set for you. What is the method of superposition? What is the use of moment area method? And what is the value of n rotations in a simply supported beam subjected to concentrated load P at the center of the beam? Now, answers for this will be given in the next lesson. Thank you. Welcome to the fourth lesson of the seventh module, which is on deflection of beams part 4. In fact, in the last 3 lessons of this particular module, we have discussed how to evaluate the slope and deflection in beams for different loading situations, considering the differential equation of elastic curve, and also we have looked into the method of superposition, how to employ method of superposition in evaluating slope and deflection of beams, and subsequently we have looked into the theorems of moment area or moment area method to evaluate the slope and deflection in beams. Now, in this particular lesson we will be concentrating on the evaluation of slope and deflection of beams employing moment area method again, but in the previous examples we have looked into for the beams where the EI value or the flexural rigidity is uniform throughout the beam. Now, here we will be considering the beams where EI may not be uniform throughout the beam, there could be variable moment of inertia, or if there is a non-prismatic beam where it is varying continuously, then what will be the values of slope and deflection in such beams. Hence, it is expected that once this particular lesson is completed, one should be in a position to understand the use of moment area method in evaluating slope and deflection of non-prismatic beams or beams with variable moment of inertia. One should be in a position to evaluate slope and deflections in different types of beams for different loadings. The scope of this particular lesson includes recapitulation of previous lesson, and we will be doing that through the question answer sessions. We will be answering the questions which were posed last time, and thereby we will recapitulate the previous lesson. Use of moment area method in evaluating slope and deflection in non-prismatic beams or beams with variable moment of inertia. Also, this lesson includes the examples for evaluation of slope and deflection in different types of beams for different loadings. Well, let us look in particular module, and in this module, as we have seen, it includes 4 lessons. In the first lesson we have discussed about the derivation of differential equation of elastic curve and its application. Then subsequently we have introduced the concept of superposition method in the lesson 2. In the third lesson we have discussed about the concept of the moment area method, the moment area theorems and its application in evaluation of slope and deflection. And in this particular lesson today we have seen the application of moment area theorem in non-prismatic beams or beams with the variable moment of inertia. Now, these are the questions set for you, that what will be the value of deflection in a simply supported beam if the moment of inertia is double, what will be the value of end slopes in a simply supported beam if the span is double, and what is the value of slope at the tip of a cantilever beam subjected to concentrated load P at the tip of the beam. Now, answers for this will be given to you in the next lesson. Thank you.